Hello, everyone. I have the pleasure of introducing you Mr. Saksham Sharma from Quant Trading. He's going to talk about a low latency deep dive of Python with CPython.
Hello everyone. As mentioned, I'm going to talk about how to look into the performance of your Python program today. We'll use Cython as a tool, but we'll see where the numbers take us. Before we get started, I do quantitative trading. I build trading systems in C++ and trading research systems with Python in New York. And I like clean APIs and clean abstractions, and I like fast code, so that's where I got the inspiration for this talk. So roughly, I want to talk about a few different things today. I want to start with just making sure we fully understand what the interpreter is doing. Then I want to set the baseline with some microbenchmarks. I'll be using the same microbenchmark techniques throughout the talk. And we'll use those microbenchmarks to understand the performance of different simplistic Python operations. We're going to use Cython to optimize some of those operations and try to make them faster. But in reality, what I want us to do is I want us to leave this talk with some better understanding of the performance of our code. What thing is supposed to take how long? People don't often talk about it, but things are faster or slower, 2.5x slower, 30x faster, but I want to talk about real numbers, like nanoseconds and all. So hopefully, that's what we should be able to get out of this talk, and perhaps look at how Cython and why Cython can make things faster. So let's get started. Python, the language we know and love, it's an interpreted language. There's something called a parser, which is reading your code token by token. It's trying to convert those tokens into some simpler instructions for this thing called the interpreter. And the interpreter is executing those instructions and maintaining some internal state about your variables and your program. That's what Python is. Or, in more technical terms, CPython. That's the program that you invoke when you type Python in your terminal, or when 99% of the cases where you're using Python, that's the thing that's running. It's a program written in C. It's a compiled program, not an interpreted program. And internally, it keeps something called a Py object, which is trying to remember the state of different objects and variables that you might have in your code. To illustrate this point a little further, I made this very simplistic and basic image. The interpreter is something that's trying to deal with the external world, and it's trying to remember the state of its internal state in these Py objects. It can deal with the external world by reading the program file, the .py file that you give to it, or it can give you some std out, or it can write to some files, interact with the GUI, write to the network, using some built-in libraries that I've kept separate here. But all of this just works together in a beautiful fashion. So this is what we mean when we say CPython. It's a program that reads your file, converts it into something called a bytecode, which is just some zeros and ones. It converts it into more optimized bytecode. Again, it can do some optimizations. And then the CPython thing just knows how to run these bytecode instructions. So this is what an interpreter is. And you might think that this sounds a lot like a compiler. A compiler reads your code. This is for all the other languages, C++ or, well, pick any, like even Golang. It converts it into something called machine code. And your CPU runs the machine code, contrasted with what we just saw about CPython, where the CPython thing is running those bytecode instructions. But we could put this all together. You could say that CPython is a compiled program. Your CPU is running the CPython's instructions, and CPython is running Python's instructions. Of course, we're going through a bunch of indirections here, so things could get slow. And that's the thing that we will investigate throughout this talk. So let's make this a little more concrete. I made a simple function here. It's adding two numbers and printing them. And Python has this module called dis, probably for disassemble. It can actually give you the bytecode for something, for any function that you have. And the bytecode really just looks like zeros and ones, but what you see here is there's a pretified version of it, so it makes some sense to us. And this is what I get if I run this thing, dis.dis func. It's trying to load the constant number 1 into the stack. It's storing it into variable number 0. It's loading constant number 2 into the stack, so on. In the end, it calls something called binary add. Then it calls a function. We don't have to read through the full details of it. But the whole intention is that, the reality of the interpreter internally, it's trying to understand code like this. You could imagine, this is completely incorrect, but you could imagine that if you wanted to write some interpreter, it would do something like read an instruction. If the instruction is binary add, then find its arguments and update some global map of your variables to contain the summation of those two numbers. You could conceive of something like it. So isn't this slow? Turns out CPUs are really fast. When you read 3 gigahertz, that means that there's something in the CPU, like a clock, that's ticking 3 times every nanoseconds. You can do a lot in 3 times every nanoseconds. So in practicality, all the slow indirection of the code that we just saw doesn't really seem to matter. The CPU is really optimized. It can do some basic arithmetic stuff like plus, minus, bit shifts, booleans, in less than a nanosecond for most practical cases. Multiplication and division are not so far off, like a nanosecond, 10 nanosecond. This is so we set a baseline, like, this is what our computer is actually capable of. You could imagine even the slowest form of division, you could probably do 100 million plus in 1 second. But this assumes that your CPU already had the numbers that you're trying to multiply or divide. You're not trying to fetch them from your hard drive or anything. This is the baseline capability of our regular computers. Okay? And again, anything 100 million plus per second in Python kind of starts sounding unbelievable. So why is there a gap between these two things? As I mentioned earlier, your CPU must know that these things are two numbers when it's trying to divide them or add them or something. But the thing is, when you write code in Python, you don't really, like, if you have a function that takes two integers and adds them, nowhere in that function did you tell the interpreter that they're two numbers. They could have been two classes with like an add operation on them, right? So there's a lot of hoops that our program has to jump through just to be able to tell the CPU what kind of addition operation to do here. And this is where we gain the flexibility, because you can write super generic code. You don't have to write types. But this is also where the Python is slower narrative comes from. It's not a concern sometimes. So these are the other set of benchmark numbers I want to talk about. The moment you start hitting the external world outside of the CPU, you start getting into millisecond land. If you have a spinning hard drive, like not a solid-state hard drive, if you want to access a file, sometimes it takes the hard drive, like the hard drive literally has to spin to the bytes that you want to read, and that thing can take a few milliseconds. So the numbers we were talking about earlier, they just pale in comparison sometimes. If your program is just doing a lot of interaction with the external world, or if you're just waiting for the user to type out some input or something. So in those cases, these things don't matter. They do matter the moment we start talking about numerical programs, and well, everyone is talking about them now, so I guess we better learn. So let's measure this. How slow is Python in all these things? For this, what I'm going to use two different tools for benchmarking. One is simply I'm just going to measure the time taken by some piece of code. But also there's this thing with Intel processors called Intel PMU. It's some assembly instruction, low-level instruction that you can, I packaged it as a Python function for this purpose locally. It can tell you how many instructions has your CPU core executed until now, starting from some undefined point. So if you call this function before and after some sequence of instructions in Python, you could get a rough estimate of how many low-level CPU instructions are being churned through that sequence of your code. As a baseline, adding two numbers that are loaded up should be something like 1 to 3 instructions if you're just writing raw low-level code. In this case, what I'm doing is I'm just going to take the average of how many instructions does it take to add 2 plus 3. Turns out 528. Quite high, right? So let's try to understand. Is it a lot? It sure is, right? Ideally, the CPU knows how to add two integers. So what is it doing? It's doing a bunch of different things. It's going to find the add function for the first number. It's going to figure out how to add b into it. It's going to read the raw integer value of b. Then it's going to run the one instruction that we really want it to run, which is the addition instruction. Then it needs to create a new Python object with the returned value and return that. So yeah, this is where we are. This is our baseline, and we're going to improve from here. To do that, I want to bring in this thing called Cython. It'll help us understand as well as optimize this thing. So as we saw earlier, CPython was converting your code into some bytecode, and then there was something called CPython, which was reading that bytecode and running it, right? So it must be using some internal low-level functionality to run that code, the bytecode, right? So why can't we just directly call that low-level functionality ourselves rather than waiting for the interpreter to do it? And maybe that's going to save us some time. So, and what if we could just read our Python code and generate those low-level function calls instead of having to go via the interpreter? And that's what Cython does. This is the picture we had earlier. And where Cython fits in is like this. You can basically build external libraries and utilities that build into your interpreter, and they can interact with your internal state of your interpreter. It can make new Python objects, or it can deal with other ones. If you have a function that you wrote in Cython, your interpreter can be configured to call that function if invoked correctly. As an example, if you write the left-hand side code on in a Cython file and you compile it, it's going to make a C function like that. It takes two PyObject stars and it returns a PyObject star. Don't get scared by the weird names, like that's just Cython's internals. If you wanted to write this code yourself, you would not write those __ pyx and all that. After that, it puts in the py number add thing, which is probably a low-level operation within the CPython interpreter. It can take two PyObject stars and it returns a third one. Maybe the addition returned an error, so then this thing can raise an error. It will assign C to that temporary variable 1. Then it'll call this built-in print function. Again, we don't have to read the full details of this, just high level. It can call the print function, check the errors on that again, do some reference counting, and then return the value. So it generated low-level C code for us. Is this going to be faster? We can check. But this is a very simplistic example, and I'm doing prints here, so microbenchmarks don't make sense when you do prints and you start interacting with the real world. So I'm just going to change this example ever so slightly. Instead of just adding two numbers, I'm going to compute the sum of the first 1,000 numbers. I wrote the same code in Python and Cython, no difference at all. And mostly people just know this is n into n minus 1 by 2, but well, Python doesn't know that, so we'll let it do what it's doing. I profiled this, and please take a pinch of salt with these profiling, because again, the exact numbers are a subject of the computer you're running them on. So this is what I get. So it seems like the runtime for the loop has been 70 microseconds for Python, which translates to 70 nanoseconds on an average for each edition. And roughly 40 nanoseconds on an average for each Cython edition because our loop was a length 1000. But the instruction counts are even funnier. That's like 500 instructions just to add two numbers, and that's what we saw earlier, so that's great. Cython definitely made it faster because the interpreter is no longer in the picture, right? We're not reading some intermediate sort of code when your code is actually running. But that's still a lot of instructions. And this is where we bring in this concept called types. The thing is, like your A and B, like you could just put a breakpoint in between your code, and you could change the type, right? Like you could just put a breakpoint and set A equals my fancy object. So objects can just change types anytime. So every single time when we're doing the addition, the interpreter has to go and check what is the type of this thing and how do I do a plus on this. If we know that we're not going to do that, why don't we just tell the low-level code that, hey, this is just always an integer. Please don't go through these fancy hoops. And perhaps it could generate direct raw addition instruction for the CPU. And this is where compiled languages shine. What you could do is, you could tell it that, oh, these are actually C-style integers. So we're putting cdef int there. And even the function argument int x, I just put an int there. And now if you look at the code that it generated, it's super simple. It's literally the code that anyone would write if they were writing very simple C code trying to sum up the first 1,000 integers. I'm also not going to let the compiler do any fancy optimizations. So I compiled this without any optimizations on the compiler. And now we're talking. It looks like it's 3 nanoseconds per loop, down from 40 earlier. It also looks like 20 instructions per loop, which is not horrible. I think we're on track. We were doing quite a bunch of different things, like breaking out of the loop, checking when the loop is finished, and so on. So this is not bad at all, right? Turns out, if you let the compiler do some optimizations, it brings it down to 600. And that totally does not make sense, right? We're adding 1,000 numbers. Like, that cannot happen. So I spent some time looking at the assembly code, what the compiler did in this case. This is all it did. For those of you who don't know assembly, all it's doing is it's doing n into n minus 1 by 2. It figured out that this loop is just that thing. So the story here is raw untyped code can be much, much, much faster. Typed code can be much, much, much faster. And especially if you let the compiler help you, you can be very fast. So looks like we're on track for figuring out how to get performance in Python. So this is complicated, right? We just introduced a new build step. We introduced something called Cython in the mix. Why should we ever do this again? The intention is that you choose between flexibility and speed when you need it. Python is a beautiful language for gluing together different pieces of your business logic. And other languages are well suited for extremely low-level fast optimizations. And we need to figure out the right balance for these things. If your program is doing a lot of database calls, you probably don't need this kind of stuff. So with that said, let's look at the case study that I had. The intention here is, let's say there's a NumPy array. And maybe it's coming from a data frame. And the user wants to access different values in it all the time. And we want to look at how to optimize it. And we're going to look at different parts of the code. We're going to think about which part can be faster. And we're going to replace Python indirections, where Python doesn't know the type of something, with more optimized and direct operations. So this is the benchmark that I came up with. This function doesn't really do anything. It just looks up some integer inside the data frame, some value inside the data frame at some integer location. It's inside some column called int call. This data frame had 2 or 3 columns. So I'm calling this inside a loop 1,000 times, and I'm going to check how long it takes. Turns out It takes 8 microseconds to access that one location inside your data frame. Now, this is really bad, right? Because we saw earlier that adding 2 numbers takes, what, 5 nanoseconds, 10 nanoseconds, 1 nanosecond, something in that range. And now we're at 8 microseconds. And that's a lot of instructions just to be able to look up something in an array. You even know the index of it. You're not trying to binary search or anything. So how do we optimize it? First, we identify that the whole operation that we're doing, like, it first needs to go and find the column in the data frame. Then it needs to convert the index into a C index, integer. It needs to look up the thing. It needs to look up where the .loc function is for the data frame. And then it needs to convert the returned integer back into a Python integer. Ideally, this should just be a lookup, right? This is not a complicated operation. Also, the loop that we saw is like slow, the same problem as we saw before, while summing up the 1,000 integers. So let's look at this. First, will Cython help if I just put this code into Cython? Turns out it doesn't, because there's not much instructions going on. Like, the interpreter is doing very little work here. It's just reading the code once and then returning it. So let's restructure this thing. So I propose that we actually allow us to cache some of the things that don't change early on. So the data frame doesn't change, so why don't I keep the data frame inside a class? And then the get function is just looking up the data frame from the class and giving returning the value. And this is not a great idea. It doesn't help. But it lets us go towards the optimization that I'm heading towards. And that's called this thing called memory view. Specifically, this is just a Pythonic way to express a NumPy array in a safe typed fashion. So you're conveying to the Cython process as well as your CPU that you're going to be accessing values from an array of integers. You're not going to be accessing values from a Python object. It's a very clean abstraction. I like it a lot. It's like you're dealing with a Python object, but in reality, you're reading raw bytes. So I just changed the previous code to actually have this thing in64 square bracket colon. This is how you talk about a typed memory view in Cython. And you can just save it in the constructor, and then while accessing it in the get function, you're just accessing from this. And this is really low level. The Cython interpreter is going to generate very simplistic code for this. 30x faster, actually, just by this one very little trick. We got down to 180 nanoseconds to look up a value in an array repeatedly. It's not bad at all. But let's try to go a little further. This also throws some nice exceptions, and this is what we saw earlier, right? So we're done with this part already, with one simple hack. What can we do more? We can move the loop into the Cython side as well, right? So now we're no longer calling a Python function 1,000 times. We're just letting Cython do the loop for us. And maybe Cython can do it a little faster, right? Turns out we get 150 nanoseconds more. And that's roughly the overhead that I've seen across multiple different benchmarks I've done for Python function called overheads. Roughly, it takes 100 to 150 nanoseconds for calling a Python function. Also, probably for converting the arguments into a C argument and then converting the final return value back into Python space. So this is another baseline benchmark number that we can have in our mental model. This is obviously a little variable, depending on all the different things that I just mentioned. Finally, the same thing we saw earlier. We could also tell Cython that the loop is typed, right? We could put the int, we could do cdef int I rather than this I equals 0. So now it knows that this I is an integer, and it cannot change type. So this is what we had earlier. And we land at this number now. 5 nanoseconds. I say this is good enough. We're pretty close to optimal here. And 33 instructions, not bad at all. We're still getting type checking. We're getting out-of-bound access checking in the array. So if you try to access something at the wrong index, it's going to still raise an exception. But you're also super fast now. So yeah, I say that's good enough. And to summarize the baseline numbers that we just talked about in this talk, if your CPU knows what it's doing, if it knows that these are two integers, you can have a mental model that it's going to take something like 1 to 10 nanoseconds, depending on how complicated the thing you're doing. If you try to do this thing in Python, like if you're adding two numbers or something, it's going to take something somewhere between 10 to 100 nanoseconds, depending on a bunch of different things. For function calls, regular C functions don't take more than 5-10 nanoseconds, just calling the function. I mean, within it, it can do whatever. The same number on the Python side is something closer to 100 nanoseconds. And the idea is using Cython and its friends, like lots of other libraries that people talk about. Pyo3 is the new popular one with Rust. We can speed up the inner loops of our program and keep the nice Pythonic API for our users, but improve the business logic part of our code to be faster. Yeah. So with that, leaves us a few minutes for Q&A. But thank you, everyone. Yeah.
Hi, thanks for the talk.
Hey.
Do you know how the performance of Cython compares with direct use of the C API?
I do, actually. I think if you tune it well, there's very little difference. I've actually done some extensive profiling on that. It has to be tuned well. The thing with C API is it's hard to use it simplistically, but if you use it, like, you basically just know exactly what you're doing, but it requires a lot of thinking. With Cython, it's like, even if you don't know what you're doing, it's still going to do something. And you can tune it well by adding these cdef ints and all that, and then it starts getting faster. So it's a question of ease of use rather than like some theoretical limitation. Cython can be as fast as you want. It depends on where you want to start. Like, yeah. Thanks.
Hi, thanks for the great talk. I have a question again about comparing Cython with Rust, because there's a lot of interest these days around rewriting parts in Rust to make things faster. So like you mentioned Pyo3. Are there cases where it's better to do one or the other? Are there cases where it's faster in Rust versus Cython? Or can Cython go like as fast as Rust in all cases?
That's a good question. I've never used Pyo3. I've used all the C++ equivalents of those things, like PyBind 11 or Boost Python and all that. I've profiled those extensively as well. My experience has been that Cython ends up being, so as I mentioned earlier, it can be tuned to bind your code to Python in a way that it's extremely performant. It just doesn't do it in the first code that you're writing. Like, the first time you're writing things, you might not be super optimized. But what ends up happening is that Cython is a little easier to consume for some Python users because it looks like Python. So some people prefer Cython because of that. But as it is, like, I don't expect any theoretical differences in the max possible speed you could get out of any of the frameworks. I think there are some frameworks, at least in C++, that are a little slower by default. Pyo3 might be that, but I haven't benchmarked it. Yeah.
Thank you.
Yeah.
Thanks for the talk. So I guess I understand like the optimizations in terms of using Cython versus Python, especially as it pertains to business logic. But have you actually found in your day-to-day, and if you can't answer this question, that's fine, that you're actually able to use Cython for like truly latency sensitive operations where you want to minimize variance, and because like you said, it could be 0 to 10 nanoseconds, but there's a certain amount of variance in that, or do you effectively just kind of have to still use FPGAs or ASICs?
Yeah, I think the moment you touch anything with Python, like the moment you touch any Python object, you bring in variance, which doesn't happen with a low-level language because you're controlling which variables are being created and so on. The only scenario where I would say I've tried to control variance with Cython has been when I write my code in C or C++, and I put Cython just on the boundary as a thin wrapper to just convert my Python objects to C and C++ and so on. So at that point, there's still some variance happening, but this is more like numerical applications where you're trying to study. So you don't care about the last nanoseconds variance. For trading, I would highly doubt if anyone is using Cython in trading, like low latency style, but yeah.
Thank you.
Yeah.
Thanks for the presentation. I wanted to ask, do you have profiling on when you use parallelism inside Cython to get around GIL?
I've done that actually. I did present that at one of my talks at CPPCon last year. But
Any insights or?
Yeah, you have to be explicit by telling Cython. In Cython, you have to explicitly say that this function does not use the GIL, and then it can release the GIL. That's just not possible while writing Python code. But with Cython, you get that free option of just writing no GIL. And then the problem is within that code, you cannot deal with any Python objects. So you convert your Python things into C. Like for instance, the while loop that I had summing up 1,000 integers, you could put a no GIL around it because I had converted my arguments to C already. So then I can do whatever. And if I have thousands of these threads running, they can all work in parallel. So it works very nicely. And it's especially useful if you're trying to, I don't know, read data from files in different, from different functions. So they can run in parallel cooperatively without hogging up the GIL. Yeah. So Cython, yeah, that's a good point. It gives us the free option of releasing the GIL if we want.
Thanks for the high information gain presentation. I feel like I learned a lot. I wanted to ask you that HW module, was that just for benchmarking things in this talk? Is that open source?
Oh no, that was just basically
just that one function for the PMU?
No, it's not even an open source thing. It's just something I wrote. Like I literally wrote it in a CPP file and.
To access the PMU, yeah.
Yeah, like
okay.
I think I just compiled that code into hw.cpp and put a Cython binding around it.
Okay, cool. So that's basically the source code right there. But anyways,
yeah, but that's just like what ChatGPT told me to do this. Yeah.
Awesome, awesome. Thank you.
Yeah. Right. Oh. Right. Thank you, everyone.